I hope we can start now our second invited lecture for today. I hope my colleague, Professor Dr. Bernd Möller is online. Okay, so I would like to announce the lecture, The Essence of Geography in Energy Science, which will be given by Professor Bernd Möller, that studied energy engineering at the Flensburg University of Applied Sciences. He worked as a research fellow at Aalborg University in Denmark, where he obtained a PhD in energy planning at the Department of Planning and Development. As a member of the Sustainable Energy Planning Research Group, he gathered experience with the energy system analysis and later on specialized in spatial analysis and the use of geographical information system in energy and environmental planning. He has been a board member of Samsø Energy Academy in Denmark on an island dedicated to 100% renewable energy supply. Professor Bernd Möller is chair of the Master Energy Program of Energy and Environmental Management at the Europa Universitat Flensburg, a program with a 25-year history dedicated to sustainable energy systems and management in developing countries. Main areas of research are renewable energy sources such as wind, solar and biomass, and the geographical aspects of sustainable energy systems in terms of technology, economy and planning. This includes studies of resources availability of biomass, landscape impact of wind energy, continuous resources, economic models of offshore wind energy, the connectivity to district heating, as well as heat atlases of demand and supply for Denmark and Europe. Hope, Bernd, you can start your lecture now. Hi.
Yes, I can.
Yeah, sorry, Paul will be soon here.
Yeah, thank you very much, Göran, for introducing me. Now, ladies and gentlemen, I'm happy to be here, and I'm really happy for the invitation to give a talk. And I have decided to let it span over 25 years or so of working in this field. And yeah, sorry that my colleague, my former colleague Paul from Aalborg is not here. And yeah, he would have been able to introduce me very well, I think. But Göran, thank you very much for presenting me. What I want to talk to you about is the essence of geographical analysis within our field of activity, and that is primarily what I call energy sciences. And I mean, if you look at this from the perspective of the past and actually look at the work, the question that we need to start asking is why geography is a part of energy science at all. And I have collected a few ideas. And first, we all know that energy demand is distributed, infrastructures are not present everywhere, and also renewable energy sources in particular are spatially distributed. And that is the main difference from, let's say, fossil fuel sources that are not distributed so much in space. Second, we know that sustainable energy systems have a much higher association to space, to location and distance than fossil fuels energy systems, which are mostly point sources and which are much better to be traded internationally because they have higher energy densities. And then thirdly, it looks as if renewable energy sources are seemingly abundant, but they are limited, and they are mostly limited by spatial constraints. So much of the currently available energy system data that we work with is only available on a macro level. That means by country, and usually they need to be disaggregated, so we can use them for local studies. So the spatially distributed energy processes that we have to do with, they also require spatially explicit decision support models, because it is always dependent on location, and location is increasingly local and regional. So the geographic dimension becomes very important for us. So in developing renewables, we go from the interest for the absolute, for example, saying, is wind energy feasible? is solar energy feasible? Are smart energy systems feasible? And we are going to the relative and the marginal when we now start planning and when we continue planning and modeling. That means it's not so much the whether something is feasible question, but how feasible and where, and how much less or how much more needs to be done. Second, we need to put an increasing emphasis on location and distribution of energy sources, on infrastructure and efficient demand in terms of amounts and costs. And that is simply because these technologies are more investment intensive. They are more critical to location in their planning. And also we see problems that arise in terms of acceptance. So when we work with energy planning decision support systems, we need to look more and more into the small-scale geographies of the present. So let's have a look at some current trends. Why we need to work spatially, and I think we can derive our motivation from some of these trends. The first one is clearly that we've seen so far an exponential trend in the growth of renewables. Looking at the last 20 years or so, we've seen a trend that is not precedented by any energy technology at this scale. And this trend seems to continue, and that of course leads to increasing questions: where is renewable energy going to continue? The second driver is the falling costs of renewable, and I've found some recent cost from IRENA, both the auction and the LSOE costs from their database. And it's obvious now that most renewable energy technologies are within the fossil fuel cost bandwidth, and some are passing beyond. That makes them increasingly competitive and increasingly interesting. And that is one of the drivers that means we have an accelerating growth in renewables. Of course, there's pressure from climate change mitigation, but I think the economic driver is much stronger now than it used to be. A rather recent trend is that we will also see competition for land, and the competition for land will be increasing. And that means if we continue to develop renewables at this pace, and if the costs keep on falling like this, we will have to look at where we can install these. And this recent paper from Scientific Reports shows that, for example, in the European Union, we see a lot of change from forestry, from agricultural land to solar land, what they call. So the same trend can be seen in other places of the world. And obviously for Europe, it's very critical to look at the high population densities within Europe, and also the presence of very high energy demands. And that leads, these three effects combined lead to future problems that we need to address as energy professionals. And I'd like to ask a few important questions to begin with. First, how can we build a quantitative basis for scenarios of energy system transition? Meaning that, of course, when we build energy scenarios, we are also always interested in figures. And these figures will look differently. They will be based on geography and on space. Secondly, we need to find out what limits the potential of distributed resources like wind, biomass, district heating geographically. And as there is always a link between geographical phenomenon like distance, location, distribution, we need to ask how much of a local or regional resource is within economic reach. But also how much is environmentally benign and how much is socially acceptable. And that the latter case is increasingly important can be seen by the resistance against new wind power projects in many countries. So if we look at the academic activity of that is related to GIS of the last 30 years, I tried to search for all papers that contain energy and GIS on Google Scholar recently. And while in the year 1990s, there were, let's say, 3 papers related to these 2 terms published every day, it is now about 100. And that, of course, makes it really difficult to catch up and to follow the activities. So this shows the increasing number of research papers. There's also an increasing number of review papers, and that's the right axis, which keeps on steadily exploring. What we see is that while using GIS for energy has been pretty exceptional in the 1990s, it is commonplace today. We see that this follows a general trend of data availability, of digitalization in general. But we also see that in the last few years, there has been an explosive growth in what this works with, and that is openly available data and information. Then we also see an increasingly complex modeling that is based on geography at increasing spatial resolution. So where the typical paper that worked with GIS 20, 30 years ago was using, let's say, local data on local administrative level, on even national scale, we now see models that go far beyond, that go into the 100-meter level resolution, for example. And what we've also seen is that GIS itself has evolved from something that people use to make nice maps into something that is now an integral part of energy research, accepting that energy systems are geographically determined. I would like to focus today on a few geospatial methods to illustrate where I see an essence of GIS in energy science. And I'd like to start with some basic methodological considerations. We do have some basic methods that are similar to other fields of data science. It's about data collection, data processing, and data management. But increasingly, it's about data sharing. We speak about more and more about open data, openly available data, and open data platforms. And visualization also is part of this basic set of methods. But visualization is more than making nice maps, or GIS is more than making nice maps. It's also about something else, and this is what I call the essence. Here I see 3 spatial methods that are central to do some spatially explicit modeling of distributed resources and how they are associated to energy systems. First, spatial disaggregation helps us to map elements that have not been mapped before, the uncharted. We see that, for example, energy demand in most countries isn't really charted. That's because it highly depends on a multitude of factors like consumer behavior, settlement patterns, and so on. And we cannot assume that all this has been mapped across the world. Second, we look at cost-supply modeling, where we differentiate between the technically available and the economically, environmentally, etc., accessible potential. This is simply there to say what is feasible right now, what is economically within reach, what is socially and environmentally acceptable. And thirdly, we see methods of spatial allocation where we match supply and demand locally by mapping both things and then using operation research to establish a match. To illustrate what cost-supply analysis is, I would like to focus on a topic that is currently being discussed in Denmark, and also Denmark being one of the countries where we've seen has spearheaded the development, and that is offshore wind energy. So in cost-supply analysis, we need 3 elements. We need a map of suitable areas, where can we build offshore wind energy or anything else. Second, the energy production, how much energy is being generated per area unit. And thirdly, what are the costs of producing this per area unit and per energy unit? So in order to do cost supply analysis, we need resources and costs and restrictions for all locations. And for this, it's very important that we use a uniform grid, let's say 1 square kilometer or 1 hectare. And then a spatially explicit supply model can be built by summarizing all the resources W at each location I and J by their associated localized costs. So it's very important to understand that both the generation, but also the cost of developing a source depend on location, and also whether it is possible at all to use a location for the generation. So that leads us to the graphic result, which is a cost supply curve. The cost supply curve draws the marginal costs over a cumulative technical potential, and it usually has a shape like this. And it's a non-linear curve simply because the costs are not behaving linearly. There are some locations that are much cheaper to develop than others, and others that are much more expensive to develop. So looking at this shape, we can establish the total potential of a resource, but not all of the potential can be utilized because there may be a fraction of the resource that is above a given acceptable cost. And that gives us the economic potential. However, things become interesting when we accept that, for example, not all of the areas are available. If it turns out, for example, that out of the total potential, a certain fraction is not possible to develop for wind energy or solar, then it means that the total potential is reduced and the costs increase on an overall level. That means we can establish a second intersection here of higher marginal costs. And it's interesting then that we have two different cost levels for the same technology, but for different users. And this would allow us, for example, to calculate the opportunity costs as the difference between these two scenarios. The opportunity cost being that the ability to utilize a certain amount of wind energy, considering different environmental regulation. So if environmental regulation is strict, then the available area is less, and then the costs are higher and the potential is less. On the other hand, we see that technologies improve all the times, that we may be able to build better wind turbines, solar converters, etc. And this would mean that the cost supply curve would look like this. The total potential is greater, and also the costs may be lower. So we have these two dimensions of continuous technological improvement and of continuous improvement of environmental regulation. I want to show you a few cases in the following where we have applied this for different fields of energy science. So first, I want to illustrate an example from our Pan-European Thermal Atlas, PETA, where we have used spatial disaggregation in order to understand how heat demand is composed. The problem is that we do not have a European map of how buildings are distributed. So we made one. This map shows the intensity of multi-story building activities, for example, across Europe on a 1 hectare level in square meters per hectare. This has been done by using regression analysis techniques where we have used already mapped phenomena, for example, population and built-up intensity, in order to derive statistically the likelihood of a certain building density. The second is that we use this to calculate the European heat demand map, and we use the heat demand map to calculate the potential for district heating across Europe. This is clearly a resource geographic exercise because not all areas are equally feasible to develop. Particularly those areas that have high heat demand densities are characterized by low development costs. So we have delineated potential supply districts, and for each of those we have calculated the costs. We've done a cost supply analysis. And we use the cost supply analysis in order to establish the potential for district heating across Europe. This is now available on an online atlas. I don't have a link to that, but you'll find it anyway. Another case where space is very important is the concept of energy efficiency. And it's 10 years ago that I did some studies on this in Denmark, because I wondered that whereas we may be able to save heating in a large fraction of the building stock, the building stock at the same time is occupied by people, and not all of which have the same means to actually build and renovate their houses. So the unequal distribution of property value, of income, and of energy supply options also mean that not everybody can join the trip of energy efficiency. So we do not have equal opportunities to reduce energy demand significantly in all existing buildings. And what you see on the map is the proportion of the property value that you need to invest in order to reduce the heat demand by 50%. And where this is not a big issue in the big cities where property prices are high, this is a serious issue in the periphery of Denmark, in the rural areas. So we see that we may have an rural urban inequity, not just across Denmark, but specifically across Europe, that leads to new problems, where we see that those areas that are structurally weak already may become even weaker in the future because they're left behind. On a more positive note here, my colleagues from Aalborg University, including our chairman, have done some studies on how we can develop low energy buildings and at the same time as low carbon heat supply. So this diagram shows the heat saving costs as the proportion of the total heat savings. So the more heat you save, the higher are the specific costs or marginal costs. However, we can also establish district heating or energy supply systems that are tailored for higher or lower energy efficiencies, and we see some benefit of doing that. And this leads to the very actual principle of the energy efficiency first, principle of the European Commission. We do have an ongoing research project, the Synergies project, where we look at this more specifically. So we look at studies of energy efficiency in the built environment as well as the supply system, and both are really determined by geography, because energy savings depend on the building stock. The potential to develop and expand district heating also is a matter of the heat demand densities. So we have used spatially disaggregated data to a large extent to look at building retrofit as well as district heating potentials. To continue with wind energy, growing acceptance problems with wind energy have their origin in the past. So some time ago, I did a study on visual influence of turbines on landscapes on a regional scale. This is pretty much state of the art for any project-based evaluation of wind energy, but it's pretty unusual to have done that for the whole region. Now, the problem is that bigger turbines are more visible over larger distances. However, planning favors them to be located in clusters, and that leads to the fact that with technological change, that after 20 years or so, most older turbines have disappeared and only the large and big ones remain. That means the visual impact will be distributed less homogeneously across the country. And what we really need is to develop planning tools that look at this adverse effect. For example, how wind resources versus availability react, because the places where many wind turbines are being installed may not necessarily be those areas where they cause little environmental impact through visibility. Looking at offshore wind, we also did some work. The problem was at the time whether we should have large-scale, far-shore development of offshore wind energy, which in fact we got. or whether an alternative case would be to develop smaller wind farms near shore. And the smaller wind farms should have a higher acceptance level because they were locally owned. So we used cost-supply analysis here to look at the benefit. And it turned out that because of the lower cost at that time, smaller wind farms were at least for a certain share of the generation more feasible than far shore installations. This is a bit outdated. In fact, I believe now the far shore scenario is more feasible, but on the other hand, it is completely disconnected from local ownership. We also looked at rooftop solar. Here we used a highly disaggregated database, a LiDAR, light detection and ranging based method, a building model of Denmark that was used to calculate the inclination and the orientation of individual roofs, and then use this for assessing the electricity generation from PV. We found that not all roofs are likely suitable and the roof area is limited, but it's large enough to cover all of the electricity demand in the country. However, since there are differences in the inclination, the size and orientation of roofs, the development of rooftop-based solar should work with a few preferences, for example, starting with the very large buildings. It all started basically some time ago, 18 years ago, basically, when I was invited to do some work in New Zealand. The problem at the time was that in New Zealand there was an energy crisis going on. At the same time, people realized they were leaving a lot of forest residues in the forests to decay. So a first study of this kind connected the resources and the locations of likely energy plants. And we drew a cost supply curve to establish how much biomass we could get to a central location at which cost. I did the same in Iceland a couple of years later. Iceland is not really a forested country, but at some time, and primarily before the economic crisis, much of the highlands of Iceland were forested. It was a tax-saving model. And the problem is, once you plant a forest, 10, 20, 30 years later, you need to do something. Doing some forest practicing managers like thinning. And that would create an amount of wood that could have an economic value. So we looked at time-dependent wood resource studies and also the logistics in a country with very little roads we had a look at. Now finally, as I mentioned before, spatial allocation is an interesting field of study. This is from Heat Roadmap Europe, where we looked at available excess heat from industry, which could be used in existing or potential district heating schemes. So by using p-median allocation of excess heat to prospective district heating systems, we were able to establish a connection between demand and supply. The problem is that supply is limited because it is based on the industrial processes applied. However, demand is basically unlimited because you can connect many buildings, many district heating systems. One limiting factor, of course, is the length of pipes that you can build and how the routing of pipes could happen. So we looked at methods from operations research to use to allocate constrained resources to the nearest customer to get a least cost potential study here. Right, doing this, we learned a few things. First, sustainable energy needs geographical studies. And this has taken the scientific world some time to understand, I believe. Second is that energy economics are determined by location, particularly if we speak about distributed resources in a sustainable energy system. Location, distribution, and distance are important, but only now with the advent of all these open source data, the world being mapped, the digitalization of many processes in society, only now we have the means to do this. I see that land conflict is inevitably when we continue to develop renewables, but it is also inevitable to include in geoscience the aspect of energy planning. So looking out, I would think that social, environmental, geographical constraints will gain importance in the field of science. Because we have many countries where the space that is available for renewables is getting limited. And when something is getting limited, it is interesting for economists to deal with. So turning relative into absolute scarcity. We see that prioritized areas are increasingly subjected to area competition. And we've seen that in those countries like Denmark and Germany, where public participation processes have been used to study or to lay out new wind farms. And we see it in other areas, for example, mentioning the NIMBY effect, that somebody has to take action, and this cannot happen fast enough. What we see often as a result is that because the most interesting, the best locations for wind energy are no longer available or disputed, that we use inferior locations. And this makes site assessment more critical. We've seen that with wind energy, that we've gone from simple wind atlas prognosis to CFD modeling, for example, to be able to assess the higher uncertainty that comes to a location. So we need more parameters to include when we do site assessment, and that is basically true for all the different technologies that we speak of. So in the future, I see there's much more relevance, of course, to this field of study, and I'm happy to continue the discussion with you now. So geospatial methods will gain importance in conflict prevention and in plannings, I believe. So thank you very much, and I look forward to discussing this with you either through the online conference portal or by email later. Thank you very much.
Thank you. Thank you, Bernd, on a very nice overview of these methods and tools and results that we can further use in our analysis. And I would like also to thank you for all your participation and development of these tools that you make available, so our students are capable to use them and make graduation thesis, etc. So I think it's quite useful. We see that now in the age of digitalization, GIS is becoming more and more important, and I think it will be essential part of all of our studies. So we have still time for discussion, and I'm opening the floor for discussion, so we can receive the questions here in the room and also online. So please.
Thank you, Professor, for your very interesting presentation. My name is Anna Lovrak. I come from Faculty of Mechanical Engineering and Naval Architecture, and I have one practical question. So could you please tell me which publicly open database you use in your work on EU level, spatial explicit databases?
Yeah. Well, that's a difficult question to answer in a short time, but basically I think the good concept is to use whatever is available. Across Europe we have very different standards of data quality. Speaking from a location in Denmark, now I can say that Denmark is perhaps ahead in terms of making public data publicly available infrastructure, and we've seen in our work that other countries like my home country Germany is lacking far behind. And that is definitely something that we should be aware of. The same is, of course, true for other countries. So the short answer to your question is, you need to be opportunistic here and just make use of whatever is available. Across Europe, the European Commission has developed quite a few nice databases. They're all available publicly through the Copernicus system. To mention a few, land use, population, the built environment, environmental criteria, and so on.
Here. No.
Thank you, Bernd, for excellent lecture. This now becomes very important tool for planning, but if we don't have this GIS databases public, then it is very difficult to do planning. Is there any idea how this could be made some like a public access infrastructure data on European Union level or something like that? Because all these layers are important, and one influences another. Information is collected, but it's not really that public. Some of it is, but in different places.
Thank you, Nevin, for this very relevant question. And this is something that I learned in the last years, and that is basically, you know, as a young researcher, primarily, you want to do it as good as you can and say, I need better data than that. And we all know the word of the saying of a bullshit in, bullshit out model. And of course, that is partly relevant. That's partly true. What we've learned in Heat Roadmap Europe was that across Europe, if there is no database that tells us heat demand, or let's say the intensity of the built environment, floor areas, all that, if we don't have that, we need to make one data set ourselves. And even though we know that this is not completely correct and true, this would be a first start. What we've seen is that I'm maybe not so happy to draw a conclusion on causal effects, but I think that after we've been working with Heat Roadmap Europe, many initiatives have been started by companies, by NGOs, by governments to improve the data collection and to improve the database for making decisions. So it is an ongoing process. We all start from zero and sometimes be below zero, and only by doing something that we know isn't good, but would get us the first couple of steps, we get the motivation to collect data. So mentioning Denmark as a case, Denmark only started to do that because they had an idea of a public information system with a civic register and so on. And only later on, because that database was available, people started to build up a similar database for buildings. But the main driver was the ability to tax property. So that's why I think a certain degree of opportunism is important here, that you just use whatever is available. So my advice is to start mapping anyway, even though you know that this is not as good as in other countries. So you need to persuade decision makers to be better. So there is something interesting going on, and that is the development in the field of open source data. You all know OpenStreetMap, perhaps, and Google data, for example. Sometimes it's the same. But this bottom-up initiative of map makers, of people who collect and crowdsource basic geodata, is a first start. This is also not perfect and not covering all areas equally, but it is, of course, a start, and it could be a good help where governments fail to collect the data.
Okay, thank you, Bernd. And what about the Inspire directive from the European Union? Because it was a framework to define the specialty planning. So are they recast, or is it?
Inspire directive has been a very important tool, but the problem is that this mostly pertains data in the public administration, which of course is very relevant. But let's say on the forefront of research data, we still need, the INSPIRE directive is often not sufficient. But the INSPIRE directive is very good because it was really there to establish a common geographic reference for basic data like administration and so on. So it is absolutely something that is valuable and should be further developed.
Okay, are there another questions? Okay, Ilya and then Ingo.
Just short question and comment. I like your sentence. Renewables are only limited with spatial aspects. We know that we have more potential than it's used, and I liked your slide with the leader for photovoltaics. Could you suggest a good study, something that we can call the solar cadastre, when we see all these limitations and how much is possible to integrate?
A solar cadastre is actually available from many places. When we started doing this with the Danish data, I found that a company from Germany was actually developing a commercial test case for Denmark on the basis of the public register. LiDAR data are available now for many parts of Europe. They're part of a general, let's say, necessity to have these systems for urban planning and other purposes. And I think we can piggyback on that and use this for whatever we think, mapping heat demands or mapping solar potential.
Okay, thank you. Ingo?
Hello, Bernd. This is Ingo from TH Köln. I like those beautiful pictures you are drawing with this GIS. And you just said when you don't have data, you just create one set of data. And I have no experience in creating those GIS and using them, but we have these potential resource maps in North Rhine-Westphalia in Germany. And when we now tried to use them to look for the PV potential on the city-owned buildings, we experience that sometimes there are deviations when we do the planning of more than 25%. So can you give any guarantee or quality indicator of GIS sources?
Yeah, Ingo, thank you very much. That's a bit of a tricky question. North Rhine-Westphalia, which is also the state of Germany where I originate from, but that's many years ago, has been in the forefront of making some of the data, like LiDAR data, available for the general public. Yes, but we are as scientists, we know that all data are full of errors, right? So I think we need to be less sensitive on that and say, okay, there is a bias, there's environmental data. I mean, in Denmark, we have this civic registry of buildings that has started to collect the actual heat demand in buildings 12 years ago, and still the database is incomplete, and still it shows deviations. So yeah, I think being able to understand the error is important. Maybe it's more important to understand what creates the error than to be actually able to quantify the error. So as long as you have a good baseline, I think it's manageable. And of course, we've always said that once we have the heat atlas, we could, let's say, do some local studies to compare that. But so far, I have not seen a single project where this has really succeeded, because the way that many local data, local heat cadastres, solar cadastres, and so on have been made is so different from the methods that we usually use. So I think you need to be a bit tough here, develop some hard skin, and be a bit fault tolerant.
Okay. Yes. Thank you. I could agree with Ingo that this is quite important, because we are assessing so many papers that are using GIS, but then they are using assumptions on some kind of data prediction or fine. But these data are available, but they are then available to certain amount of people. For example, like electricity consumption. We know now we have smart meters, but companies do not provide this data. You know, so this is, let's say,
this is of course a problem. I mean, if you look at macroeconomic data, or let's say the energy consumption within the whole country, the actual error margin is basically zero, because all millions of households are just accumulated to one. So if we have a model that tries to predict a single household, let's say with a simulation technique, Intrinsis or any other tool, we see there are great diversions. So in most studies that we have done, we look at aggregation levels of, let's say, 10 to 1,000 households in one area unit. And there we usually see error margins of 20, 30%. But the same is true for, if you, for example, look for disaggregation of time series data. So if you have a load profile of a single household or a single village or the whole country, the differences are really different, really remarkable.
Yes, but let's say there should be more error analysis. So, but yes. Thank you. Okay. More questions, maybe from online audience. Yes. Okay.
Okay. Okay, so we have a couple of questions from the Q&A session from online audience. First is from Akira Kishimoto. Is CHP infrastructure well developed in Denmark, and how do you consider on cooperation with other countries in the use of renewable energy?
Can you specify that question? That sounds like a very general question. Cooperation on data, perhaps?
Well, this is what we had as a question.
Yeah. Yeah, then I need to make up an answer. And I think cooperation is very important. We've seen that in our European projects as well, since we all come with different experiences from each of the European countries that we originate from. I believe the main advantage is that we can learn from each other. There are differences in how countries do analysis, how they collect data and so on. And I think being in one room, being in one project can actually help us learning from each other very much.
Yes.
Thank you. Another question from Deepa Manolan Kandi says, I see most of the site suitability studies through GIS uses weighted summation, particularly if it involves many criteria. However, weights bring heavy trade-offs, and the results can be very subjective. In your opinion, how practical is applying weights and using suitability maps as basis for planning in reality?
It is really difficult to understand you because there's an echo somewhere. But as much as I got from the question is weighted averages should be disaggregated as well. So we are always looking at parameters that are locally present. So for example, the distribution of building mass on a 1 hectare level, or the wind energy potential on a 200 meter level. And then additional factors that mean that this location deviates from the average. But of course, there are global assumptions that we need to take for granted because basic data don't exist for the locality. But the advice is to look for as many variables that are mapped and can be mapped geographically that describe a single location as possible.
Thank you. There is another question from Soma. How to make data projections for the future, particularly related to energy demand in a built environment in a high spatial resolution. Available maps and databases mainly show the current spatial footprints of buildings, which will most likely change significantly in the long-term future. Then the issue is also linking this demand with prospective energy supply sources.
Yeah, this is something that is really exciting, and this is really what we're currently doing. So a couple of weeks ago at the Sustainable Energy System or Smart Energy Systems Conference in Copenhagen, I was presenting a paper on that. Actually, we're trying to do that. Currently, we're trying to map the future heat demand across Europe, which includes the location of likely future built-up areas. On the basis of empirical development from the past. So we have time series of using satellite images or interpreted satellite images that show the extent of past settlements in Europe, dating back to 1975 and to 2015. So if we take this as a learning function and use some regional statistics, or let's say focal statistics, where we look at neighborhoods, and if a neighborhood, for example, has been very successful at attracting new people in the past, the trend may be the same for the near future. So it's a bit of a conservative and linear approach of predicting future population, but so far we've seen that I've seen some very promising results. And then in our Pan-European Thermal Atlas, we will also be able to calculate future heat demands in those areas. Every new built area, for example, will be developed with current building standards across Europe. And we also map the relationship to a potential future supply system. The thing is, it's always going to be the question whether an area will be supplied with individual heat pumps or with fourth generation district heating. So please expect some results from the Synergies project that we're currently finalizing.
Thank you, Bernd. Okay. So if there are no more questions, our time went up, so we are now approaching to the closure of this invited lecture. Bernd, thank you very much for all of these conclusions and for very nice answers and very good presentation of GIS. Hope we will see each other soon somewhere in Europe or around the world, but I hope you will come in 2 years in Dubrovnik again. Okay. So,
yeah, I'm looking forward to that. Thank you very much for the invitation, for taking over the hosting of this session. And hard to promise anything, but 2 years in Dubrovnik sounds like a good idea. Thank you all.
Thank you. Thank you.
See you here.
Thank you.